able to define key terms and concepts in your own words, so key terms and concepts of NTFS in your own words. You should be able to explain how NTFS manages content and metadata in your own words. To use forensic tools to extract and interpret NTFS-specific information or data structures, reconstruct a deleted file, examine NTFS structures to detect data hiding, and forensic implications of NTFS features like alternate data streams or journaling. Okay, so let's start with fundamentals and concepts. Yeah, so I already told you that NTFS means New Technologies File System, and that it is the standard file system of Windows. I think it started with Windows NT. Yeah, but I'm not quite sure of that. Yeah, but basically it's the successor of FAT32 and nowadays the standard file system for Windows. There's also REFS, which is the successor of NTFS and I think the plan was to roll out REFS as a standard file system for Windows, but Microsoft didn't do it. They only give you the option to use REFS when you install your Windows operating system. But for Windows servers, I think it's the standard file system now. But for users, basically, they didn't do it. So for home PCs, NTFS is still like the thing that is used. And you have a maximum theoretical volume size of 2 times 64 minus 1 clusters. So plenty of space to store data. And the design aim for NTFS, especially compared to FAT33, was more reliable data structures, more security features, scalability, and usability for large file systems. It's a relatively good designed file system and also offers more features than FAT and hasn't the limits of FAT. Yeah, but as with, for example, DOS MBR, NTFS has no official specification. So everything we know about NTFS, and this also holds for REFS, by the way, everything we know about these two file systems, we know from reverse engineering. Yeah. So there's no official specification that you can have a look at in case you think, I don't know, Brian Carrier made a mistake. There are many scattered sources as I said, as we don't have a ground truth, we basically have to trust that the people who did the reverse engineering did a good job. And but I mean, nowadays, so NTFS is also nowadays a little older. So if there would have been some mistakes, they would be probably known by now. Yeah, but yeah, we cannot be sure because there is no official specification. There's one problem, and that is that it is difficult to distinguish between file system behavior and application behavior. So different applications, also different file system drivers, they behave differently, and therefore reverse engineering file systems can be complicated. And it is often unclear what a valid NTFS actually is. So, or in reverse, what an invalid NTFS would look like. Yeah, and also there's always the possibility that Microsoft, for example, changed stuff in NTFS. But I think since they moved on to REFS, the chances are very low that they change NTFS in a very great manner or big manner or such that like everything would work differently. Okay, but we have to keep in mind that this is possible. Okay, what is the basic concept of NTFS? The basic concept of NTFS is that everything is a file, like every configuration file, for example, or settings of the file system itself is stored in a file in the file system. And this is a concept that is pretty unique, that you don't have with other file systems. As I said, also file system data is stored in files, and these files are hidden from the user, so they cannot be seen from an application level. But if you know where to look at, you can find them in the file system if you, for example, use the Sleuthkit or Hex Editor. And for these files, there are special file naming conventions. So they usually start with the $sign and like capital letter and then some lower letters. Of course, there are exceptions as always. For example, $MFT or $MFT mil. There you have 3 capital letters. Here you have 4 capital letters and then some lower letters. But usually they look like that. So if you see something like that, then you know, okay, this is a file, a hidden file that stores file system data. And they are not to be confused with attributes, which look like that. The naming convention for attributes is $ capital letters _ capital letters. This is especially confusing in the bitmap case because there is a file that is called bitmap and an attribute that is called bitmap, but you can distinguish the two of them through the naming convention. You will see what I mean like while we continue talking about NTFS, but just to make that clear in the beginning so that you are not too confused if I talk about a file or attribute. Yeah, this is how you can distinguish them. Okay, so let's talk about the layout of NTFS very quickly. So the thing is, there is no strict or standard layout. You can assume that the first sector contains the boot sector or the boot code. This is, I think, the only thing that is fixed in NTFS, and all the rest of the file system is data area. And since everything is a file, like also the file system configuration files could, in theory, like be localized anywhere here. Like this is the only thing that is fixed. And as with FAT, the data area is organized in so-called clusters, so sectors times 2 times 4 times whatever. And yeah, so usually in the beginning, you have the MFT. The MFT is the central data structure for NTFS. The MFT stores everything that you need to know about files and the file system. And usually 12.5% of the file system are reserved for the MFT. And only in cases where the file system is pretty packed and pretty full, the file system also allocates data in the MFT area. The MFT area don't take that too serious. There is not like in FAT, there is no area, a fixed sized and fixed location MFT area. So the MFT area is that the space that is allocated by default for the MFT, but it could be anywhere. Okay, so what is the MFT? As I said, it's the most important data structure in NTFS, and the MFT also contains an entry about itself. So the first entry of the MFT is actually the entry for the MFT. and the MFT file. And the MFT file is, you can recognize it through the $ MFT. And that file contains all the information about the MFT itself. So it's a self-reference. And because I said the MFT can be localized everywhere in the file system, we of course need to find it somehow. And this is the starting point in cases where you want to analyze NTFS. So you first have to look for the boot sector, which is the data structure in the beginning of the file system. And the boot sector contains the start of the file system data, so an entry where to find the MFT. And in the MFT, you have to find the entry for the MFT itself, and then you know everything about the MFT that you need to know. And the MFT also contains information about all files and directories in the file system. Each file and directory has at least one entry in the MFT. It can also have, or files or directories can also have more than one entry in the MFT. We will talk about that later. And in theory, the MFT could grow indefinitely. So the more files and directories one has in a file system, the more the MFT grows. And there's no fixed size for that, like a limit for the MFT size. And new MFT entries are either appended or old MFT entries are reused. And at least in my experience, they get reused very quickly. And more often than the entries are actually appended. I think they are mostly appended when the MFT doesn't have much entries to reuse. Okay. So this is how an MFT entry looks like. Each entry is of size 1 kilobyte. Only the first 42 bytes of an entry are permanently defined, like you have an MFT head in each entry. As I said, which is of 42 bytes. And you usually have like an identifier or magic byte special string in the beginning of the head, which is either file or bad. I think I don't have to comment on that. Like it's pretty clear what it means. And the rest of the MFT entry is a collection of attributes or a sequence of attributes. And attributes are basically name value pairs. Let me check my notes very quickly. So you have the MFT entry with the header. Also, the file string is also used for directories. So not only for files. File basically means, okay, it's a valid entry for a file or a directory, and bad means like it's an invalid, it's a bad entry or not used entry. And after the header, you have the sequence of attributes. And then there can be some unused space after all these attributes in cases where the entry is not fully used. In cases where all the space of an entry is actually used for attributes, files and directories can allocate another MFT entry in order to have more space for more attributes. And we will have a look at important attributes later. The 1 kilobyte size can be changed in the boot sector, but usually it isn't changed. Usually it's 1 kilobyte and it stays 1 kilobyte, but in theory it can be changed in the boot sector. Okay, let's have a look at the MFT entry addressing. So how can you find a file, for example? So if a file is to be addressed, you need the file number first. Yeah, so the file identifier, if you want to put it that way. So if we give me a second. Okay, yeah, so MFT entries are numbered consecutively starting from 0. That's the file number. And the number or the address is a 48-bit value. And as I said, the MFT can grow gradually, indefinitely. Yeah, so yeah, you have these reference numbers for every single MFT entry, and you also have the rest of the 46-bit reference address. There you have a sequence number, 16-bit sequence number, and the sequence number is incremented every time the content of the entry changes. Yeah, so with each new commissioning of the entry, the sequence number is incremented. And this is especially relevant for forensics because you can draw conclusions from the reference number. Okay, so you can use that reference address to find the MFT entry in cases where you know the reference address. And so together with this sequence number or these incremented values here, you have the 46-bit reference address that should be unique. Yeah. Okay. Okay, this is the slide I actually thought that would come after that slide, so I was a little confused, but okay. So much for the MFT entry addressing. Actually, the more important thing are the MFT attributes. I already told you have the head and then you have the sequence of attributes, and there are basically two kinds of attributes. We have resident attributes and non-resident attributes, and these attributes contain further information about the files and directories. Each attribute consists of a header, 60-byte header, and some content. Each attribute has a characteristic number or type identifier. We will see that also later, and an attribute name. And the attribute name, we had that like in the beginning. Where is it? Here. Always starts with the dollar and has this naming convention we already talked about. And so what does resident and non-resident actually mean? So non-resident attributes contain a reference to a cluster that stores the actual data. So here you can see the non-resident attribute has a cluster run 1 and a cluster run 2. And the cluster run defines where the content of that attribute can be found. And resident attributes, they store their content in the attribute itself. Yeah, and attributes are always sorted by their type identifier. So if we would have like 3 attributes in one MFT entry, then they would be ordered according to their type identifier. Okay, so the attribute header contains like generic information for all attributes. It contains, for example, the type identifier, which is important to identify the type of the attribute, but also important for the order of the attributes. It contains the size of the attribute, the name of the attribute, and a bit or flag whether the content is compressed, encrypted, or resident. Yeah, and some attributes can have a unique name. Some don't have a unique name, like bitmap, for example, or data. And yeah, this is necessary if same attribute type occurs multiple times, which is the case for the data attribute. And yeah, also for alternate data streams, and we will talk about that in a second. Okay, so the actual attribute content is not regulated and can have any shape and size, but of course there are standard attributes or standardized attributes which you will see very often in the wilds. I think yeah, I actually never saw custom attributes that are not the standard attributes, but it's possible. So you should be aware of the fact that there's no official standard for that, and you can come up with your own attributes if you want to do that. Yeah, that I already told you. So non-resident attributes are stored in clusters, and the attribute header contains the cluster run list. And this is actually a very efficient representation or storage version, kind of storage management system. And if you see that the first time and try to calculate where the cluster runs is, it seems to be complicated, but actually it's pretty easy when you know how to do it. Okay, so here you can see a couple of standard attributes that you may already seen in the exercises. So you usually in an MFT entry, you usually have the standard information attribute, which has the type identifier 16. It contains information about the owner, timestamps, access information. You usually have the file name attribute with the type identifier 48. As the name says or suggests, it contains the file name and also timestamps. The next one is the data attribute that I already talked about, like very briefly. It has type identifier 128, and it contains the actual content for files that are resident. And you can also have several data attributes. So this is the attribute or one of the attributes that is not unique in the MFT header, MFT entry, or does not need to be unique. So you can have several data attributes. And another example is index root, which is the base of the index tree of the MFT entries for directories. Okay, and data does not necessarily have to be organized as a tree. Yeah, that I already told you. Attributes are stored in ascending order by type identifier, and attributes can occur several times. So if you want to read more about attributes, as I said, Brian Carrier is, or the book of Brian Carrier is the place to have a look at. There's a question in the chat. What does resident mean? We will talk about it in a second. Okay, the good thing or the interesting thing about attributes is that attributes can be used very flexible. So here you have like the typical structure of an MFT entry. Several MFT entries can be concatenated if there is not enough space for more attributes. Yeah, and so the base entry contains a list of the attributes, so that's depicted here. Yeah, so in cases where you need more space for more attributes, there is a special attribute in the first MFT entry, so the base entry, that tells you where to look for more entries with more attributes, which is pretty interesting, pretty cool. As I said, it's a concept that you don't have in other file systems, the file concept and the attribute concept. So you can, yeah, concatenate MFT entries and have like indefinitely many attributes, as many as you need to describe your file or directory. Yeah, and the interesting thing also is that it's possible to combine attributes in the MFT entries almost arbitrarily. For example, directories can also have a data attribute. You can have multiple data attributes. You can have multiple data streams, so alternate data streams, which we'll come to also later in one entry. Yeah. Okay, so the base MFT entry, as I said, is the entry where you can find the information about the additional attributes and the additional MFT entries. Yeah, so in cases where one MFT entry is not enough, the first MFT entry becomes the base entry, and then the base entry contains the references to other associated MFT entries. And this is realized by the attribute list attribute. Yeah, I think I already told you everything you need to know about that, but in cases you want to yeah, read it again, here you go. Okay, I also already told you, like very briefly, that MFT entries can be compressed, they can be sparse, they can be encrypted, or at least some attributes can be encrypted. So we talked about sparse, what that means already last time. So you can have sparse cluster runs, for example, in cases where you have a non-resident file, so a file where the content isn't stored in the MFT entry itself. So again, resident means the content of the file is stored in the MFT entry itself, in the data attribute, and non-resident means that you have the file content stored in clusters and the attribute contains the cluster run list. And in case you have a non-resident file and the cluster runs contain many zeros, then you can, for example, say, okay, I want to have sparse cluster runs. The data attribute, for example, can also be compressed at a file system level. There is no specification of which compression algorithm has to be used, so that's bad for forensics, actually. And the data attribute can also be encrypted. Then you have to have an additional attribute that contains the necessary keys, and the keys are also encrypted. Okay, so important analysis tools for NTFS is, for example, NFI.exe. So yeah, NFI, the NFI tool, which displays NTFS details in the running system. So this is something you can do on your own PC, for example, in cases you want to know more about your NTFS file system. Of course, you can also use the sleuthkit for that analysis and display, for example, the attributes of a specific file by using istat. I think you already did that in the exercise. Is that correct? Can somebody put it in the chat? Is that correct? Okay, Autopsy did it for us. Okay. Okay, but you all know that Autopsy is based on the SleuthKit, right? So the SleuthKit is the command line tool that builds the backend for Autopsy. So implicitly, you probably did it. In case you want to do it explicitly, then you could, for example, use Kali Linux because Kali Linux already contains the SleuthKit and try out, for example, the start comment in the command line with the images from the exercises that you already have. So there you can, or with that comment, you can display all the attributes and have a look at them in more detail if you want to practice that. Okay, so 2 weeks ago, we talked about the data categories, the file system data categories according to carrier. There are 5. Let's go back to that slide. Can anybody tell me the 5 data categories according to carrier that we can use to describe our file systems? Anyone? We have 5 categories that can be used to describe file systems. And they also help us, for example, to define unified interfaces for tools. Does this ring a bell? We have data that describes the file system itself. Yes, file name, file content. Yeah, file system, file name, content, application data. Yes, there's one missing. What else? One very important category is missing, metadata. Awesome. Okay, you got it. So, as last time, we will now discuss every single category. So the data. Okay, let me start again. So we will now continue to discuss NTFS data according to these categories. And the first category we'll start with is file system data. So we now got an idea on fundamentals and the basic concepts of NTFS. So everything is a file. You have the MFT. The MFT has an entry stored in the MFT for every single file and file system, and MFT entries can have attributes. And the attributes describe the file. So that's the fundamentals and the concept. And now let's talk about file system data in more detail. So what we have in NTFS, and I think it's a little misleading, the name, or it's a little confusing. We have file system metadata files. This is how Microsoft calls them, or Microsoft calls them metadata files, but these files are actually files that store data about the file system. So, for example, the $MFT file is a file system metadata file. And in order to distinguish file system data from file metadata, Carrier calls them file system metadata files and not metadata files. Do you know where this is going? So I don't want to call them metadata files because it's these files. they do not describe files, they describe the file system. So this is why we will also go with Carrier's definition and call them file system metadata files, so FSM files. And the first 16 MFT entries in the MFT are reserved for these FSM files, so the files that describe the file system. I already told you that they always begin with the $sign and at least one capital letter, and they are usually hidden from the user. And these files, these FSM files, also have, of course, because they are regular files, they have attributes like, for example, standard information. So they also have timestamps. And they also have attributes that the naming convention looks like that. And the timestamps of these FSM files, they indicate when the file system was created. So in cases you want to check that, you can have a look at the standard information attribute of, for example, the $MFT file. Okay, and as always, we have different behaviors dependent on the operating system. So for Windows NT and Windows 2000s, the FSM files are located either directly behind the boot sector or in the middle of the file system. And for XP, we have the FSM files behind the boot sector. And there is some kind of limit where the rest of the file system starts. And for Windows 7, 8, and 10, we currently don't have any information about where the file system metadata is stored. But I already told you that if you can access the boot sector, then you get the information about where the MFT is located, and then you can search for the MFT entry for the MFT, and then you have everything you need. In cases where the boot sector is missing or you cannot trust the boot sector for some reason, then you could search for certain data structures. Of course, it's easier when you know where to look at, but basically for newer Windows versions, you have to guess where the MFT could be. Okay, so I already told you the most important files file is the MFT file, and there's also an MFT mirror file. So basically a copy of the MFT. The MFT file always has an MFT entry, which is the 0 entry. So the first entry in the MFT is usually reserved for the MFT file itself. And you need that file in order to find all the other files. And the MFT mirror is basically a copy of the MFT, has the MFT entry number 1, and the MFT mirror is usually located, or the data of the MFT mirror is usually located somewhere in the middle of the file system. Then you have the boot file. So we will now talk about the most important file system metadata files. So we already had MFT and MFT mirror. So the next one is the boot file. It contains the data of the boot sector. You can find it via address 7 in the MFT. The boot sector or the boot file is the only file that has a static layout, so it looks always the same. The first sector of the data attribute of that file is always the first sector of the drive. We saw that already here. And the structure of the boot file is very similar to the structure of the boot sector of FAT, which makes sense because NTFS is the successor of FAT, and you don't have to invent the wheel again for every single part of the file system. It also contains the magic byte or the signature that you already know from FAT. And there's also a backup copy at the end of the file system of the boot file. Okay, let's have a look at the boot sector very quickly. So in case you need to analyze the boot sector with an hex editor because for some reason you cannot use tools, this is how the boot sector looks like. And what you can do with that is, for example, you can calculate the size of a sector. You can find that information here in the boot sector. In this case, we have a size of 512 bytes. You can also check out the size of a cluster. This information is stored after the size of a sector. So in this case, one cluster consists of 8 sectors, so 4096 bytes. You also have information about the first cluster of the MFT in the boot sector. But what can you recognize here? What should you recognize here? Can somebody tell me what's important about that value? Which format does it have? Exactly, little endian. So the first cluster of the MFT is that value and yeah, not that value. In case it would be that value, the file system would be pretty big. The boot sector also contains information about the size of MFT entries. I already told you that this is usually 1 kilobyte, but you could change it if you change that value in the boot sector. And yeah, is that correct? Yeah. In order to change that or in order to calculate that, you have to use the two's complement. I guess you know what that is. Okay. Okay, so much for the boot sector. Now you know how it looks like, and you should be able to analyze it in a hex editor, or at least extract like the important information from the boot sector with an hex editor. And especially in the boot sector or the boot file, this is very important because, as I said, you need that kind of information for every step after the boot sector analysis. In order to proceed with your analysis, you need to have the information from the boot sector. So in cases where you cannot analyze that file with tool support, you should be able to also extract that information with an hex editor. The fourth important file system metadata file is the volume file, which contains the drive name. It has the MFT entry 3. The drive name or this volume file has a special attribute which is called volume name, where the drive name is stored in, and the volume name and the volume information is reserved for that file. So you should not find that anywhere else. Then we have the attribute definition file, which contains the name and type identifiers of all attributes in the data attribute of that file. So this file contains the information about the attributes in its own data attribute. So in cases where you are not sure if there is an attribute, a custom-made attribute that you don't know much about, you could, for example, have a look at that file and analyze the contents of the data attribute in order to find this special or custom attribute. Yeah, and there's a chicken and egg problem, how to read the attribute definition file without knowing the type identifier. Yeah, so you should, or you can assume that default values are used, and you should use them for the first read. Yeah. In theory, it is flexible, and there could be a case where the standard or default values do not apply. Yeah, then you have to basically analyze the MFT and try to find that file manually or with the help of an hex editor and have a look at if you can find the data attribute of that file with the information about the attribute lists. But practically, it's always the standard case. Okay, there's another file, the bitmap file, and this file shows the allocation status of each cluster in the file system. And for each cluster in the file system, there is a bit which indicates with 0 or 1 if it's allocated or not. This is a pretty important file. And then we also have a bad cluster file, which stores information about whether clusters are damaged or not. As with FAT, usually or as with every file system nowadays, usually your hard drive or your storage device handles damaged clusters. So in that bad cluster file, there shouldn't be too many damaged clusters. Otherwise, it's very unusual. And as the bad cluster file contains many zeros, the data attribute is sparse. So keep that in mind in cases where you want to analyze that file. Okay, how should you proceed, or how should you analyze file system metadata files? So as I already said, first analyze the boot sector and have a look at the copies if necessary. Then read out the MFT or the MFT entry for the MFT and then the MFT. You can also have a look at the MFT mirror if necessary, if something seems fishy. And yeah, so there could be a limited amount of data hidden in the boot sector or at the end of the MFT. But for data hiding purposes, it's not a very good space because the growing MFT could just override it. Yeah, have a look if you find unusual attributes or yeah, further data hidden in attributes. Okay, let's continue with content data. Are there any questions so far? Okay. Then let's continue with content data. We already talked about clusters. The beginning of the drive starts with cluster address 0. And each cluster can be assigned to any file except of cluster 0 because it contains the boot file. Or drive is maybe a little bit misleading here. So the file system starts with cluster address 0 and the cluster 0 is reserved for the boot file. Then we already talked about the data attribute. The data attribute actually stores the content or stores the actual content of the file. There's no native structure for the data attribute. One important thing to know about the data attribute is that it is resident in cases where files are have a lower size than 700 bytes. So in cases where the file is bigger than 700 bytes, it becomes non-resident. And in the non-resident case, the data attribute stores the cluster or data run list. And in cases where the files are lower in size than 700 bytes, the data attribute is resident and stores the file content itself. So now that you heard this term like a couple of times, we should actually discuss how a cluster or data runs work. So the cluster and or data run list, it depends on which source you use in order to define this term. Some call it a cluster run, some call it data run list. But it works always the same. You have a defined offset for the data header, and then you have 2 bytes in little endian that define the position of the first element in the cluster or data run list. So the structure is as follows. You have the 2 bytes, and in the first byte, the least significant nibble tells you something about the run length of the cluster data run, or the cluster run, the data run. Let's call it cluster run. And the most significant nibble tells you something about the run offset. The second byte is null x or 0x00 if this is the end of the file, or it contains the next cluster run list element. And the first cluster run list element contains has the address relative to the start of the file system. It stores the address relative to the start of the file system, and further elements address or contains an address relative to the start cluster of the previous element. So the first address is relative to the file system, and the second address is relative to the element in the list before that element. I know it sounds complicated, but we will have a look at an example, and then I think it becomes clear. Okay, so let's say this is our cluster run, or our data attribute that stores a cluster run. We have the attribute type identifier in the beginning of the data attribute. It's 128, and it tells us that it's a data attribute. Okay, then we have our offset data run list, which is stored here. The offset is 64. So now we know where to look for our cluster run list. Okay, now that we know where to look for the cluster run list, we have to have a look at these bytes here. So the red value or the red frame, so in the red area, you can find 3 bytes for the cluster length. So in this case, we have this number of clusters which belong to the file. And then we have the address for the first cluster. This is the first entry of the data run list or the cluster run list. Then we have the second entry of the cluster run list, which tells you again, or us again, how many clusters we have. And then the address relative to the address in the first cluster run list. And then we have a subsequent 0, which means after that, it's the end of the file and we don't have to look for any more cluster run list entries. Okay? Are there any questions? I mean, maybe when you have a look at it at home again, it should be fine. Okay. Then there is something that is called alternate data streams. You heard about that term already in the beginning of this lecture. And what does it do? So imagine you have a situation where you have a file which is called foo.txt, and it has an MFT entry, of course, with a head and some data attributes. And the as I told you already, the data attributes are unstructured attributes, and you can have more than one data attribute. And in cases where you have more than one data attribute, more than one resident data attribute, this is called alternate data stream. So the first data attribute may contain a string hello, and the second one may contain a string blah. And but it also contains like an additional file name. So this is the regular data attribute, and this is an alternate data stream. And this is very well suited for hiding data. And yeah, I can show you in a second how this actually works. So this is how you create an alternate data stream. You basically, when you do that, you basically create a new data attribute for the same file. And let's say you have this file hidden.txt, and in order to create an alternate data stream, you concatenate the normal txt file and the hidden txt file name. Let me check my notes very quickly. Yeah, so what you do is in the command line, you can use that type comment and the name of the new hidden data attribute that you want to create. And with that sign and the concatenation of the names, you create the additional data attribute, and you can do it as many times as you would like to do it. As I said, there's no limitations of how many attributes you can have. And in order to show alternate data streams, you have to use that concatenation again. Then you can have a look at the actual contents of that alternate data stream content. Yeah. Okay, let me check my notes very quickly. Yeah, I think I told you everything that you need to know about that. Okay, for the analysis of NTFS, it's also important to know how MFT entries are allocated. So the regular MFT entries they usually start with the entry address 24. And if an MFT entry is deleted, for example, when a file is deleted, the only thing that changes is the header, and the header then contains a bit that indicates that a file has been deleted, but all the other data remains unchanged. So in cases where a file is deleted, you can still have a look at the MFT entry and have a look at the, for example, standard attribute or the file name, or also in cases where the file is a resident file, you can have a look at the contents of the file and also the alternate data streams, for example. And I already told you that MFT entries are usually reused. You can append them at the end of the MFT, but usually they are reused and they are reused very quickly. So chances are there are a chance that you can still have a look at the contents, but you have to be quick, or the deletion should not be too long ago, because otherwise the MFT entry is probably already reused. As I already said, new MFT entries are rarely created, and but it's always like a good idea to, in any case, have a look at or look for MFT entries that point to deleted files and check out the contents of the MFT entry. And the allocation strategy of course, depends on the operating system and the file system driver, but that's the usual behavior. Okay, in cases where you want to analyze file contents, you should find and analyze the MFT entry for that specific file. Then you can have a look at the data attribute and either see the content already or analyze the cluster run list. You should always also view unused MFT entries, because they may be like old entries from deleted files that you can use for recovery of the files. There can be slack space, and remnants of old files in the slack space. Windows zeroes out the next full sector when writing files, but not the cluster. So in both NTFS and Windows, there's a good chance that you can find slack space and maybe old file content in there, and you should be aware of alternate data streams. What you can do further than this is you can have a look at the bitmap file and see if you can find any unoccupied clusters that you want to have a look at. You can, in order to do that, you should read out the data attribute of the bitmap file and check out the cluster status and then the clusters themselves. And here, or in NTFS, data can be hidden in the clusters that are marked as either unused or marked as damaged. And if you want to have a look at the damaged files, you should check out the bad clusters file. Okay, questions? If not, we will discuss NTFS metadata next. So one or the most important metadata type in digital forensics is timestamps. And there are 4 timestamps in NTFS for every file. We have the MAC time stamps, of course, but we also have an MFT modified time, which stores information about the last update of the MFT record. And Yeah, this is the usual timestamp format for NTFS. You have a 64-bit integer value, and you have a number that gives you the time in nanoseconds, since the 1st of January in 6001. Why they use that year remains a mystery. Nobody knows. Back then, there were no computers. We don't know. It's just a weird design decision that we have to live with. Yeah, but in cases where you read out timestamps manually, you should know that this is the reference year, the reference timestamp, and the value gives you nanoseconds since then. Okay, and there are, of course, different operating system behaviors as always. And for example, Windows Vista updates the last read access time by default for performance reasons, but this does not necessarily mean that every Windows version does that. And you should also be aware of the fact that the standard information attribute, which stores the file, the timestamps for the file, can be modified by user-level processes. For example, you can use tools like Timestomp to manipulate the timestamps. And the file name attribute also contains timestamps, and these timestamps can only be modified by the system kernel, so not by user-level processes. So in cases where the standard information attribute contains the same timestamp or very similar timestamp for mass of files, then this can be a hint for the usage of tools like Timestomp. And then you could have a look at the file name attribute. Okay, yeah, as I said, the most important information in standard information attribute is timestamps. The MFT modified time is usually not displayed or shown to the user. And if you want to have a look at the standard information attribute, you can, for example, use the sleuthkit command istat. And the file name attribute contains a reference to the parent directory, which is useful if you want to track a random MFT entry. It also contains timestamps. They are usually not regularly updated, but as I said, they can only be changed by the kernel or the system, and therefore you could check them out in cases where you think like, I don't know, these timestamps in the standard information attribute, they look weird. Then you can have a look at the timestamps here. Yeah, they usually indicate, especially when a file was created or only when a file was created, because they are, as I said, not usually updated, but they can be used for a sanity check. And of course, the file name attribute contains a file name. And this brings us to the file name data category. The file name attribute contains the file name in an UTF-16 Unicode, but you can have an additional file name attribute to store like a regular FAT32 file name in the old 8.3 format, so 8 characters of file name, 3 characters suffix. Yeah, and there's also this directory B tree, so the index root and index allocation, which also contains file names. And we can talk about that very quickly for a second. So the NTFS file system allows file contents to be stored efficiently in a sorted order. The main application of these B trees is directories in which the entries are sorted alphabetically. And there are two B tree structures: index root, which is a resident attribute that contains the root of the B tree, which is used to organize the directories, and a small number of index entries. And there's index allocation, which is a non-resident attribute that contains a large number of tree nodes, and each with many index entries. And there's also the bitmap attribute in this case for managing the allocation status of the index entries. And these B trees are very complex. If you want to know more about them, then you should probably read the Brian Carrier book, because explaining these B trees, yeah, as I said, they are very complex, and in like the regular, we want to analyze files and file contents case, they are also not, you don't necessarily have to analyze these B trees. But yeah, just that you know they exist. They are complicated. They can, of course, be analyzed. The SleuthKit will not analyze them. Autopsy also doesn't analyze them, I think. So this is manually work that you would have to do in order to analyze them. And how to do that, you can read in Brian Carrier's book. Okay, so in order to analyze important metadata, or the most important metadata, you can do the following. For example, if you want to list all files, you should try to find the root directory, which is located in the MFT entry 5. Then you can start traversing the B tree in index root, but the SleuthKit does that for you. So you can list all the files in an NTFS file system with the SleuthKit, but the SleuthKit just gives you the information about the files and not additional information about the B trees, for example. But what it does is it starts traversing the B tree in index root. Index allocation is also included in this traversing process and analysis process. And yeah, so this is what the SleuthKit does to show you all the files in the file system. You could also do it manually, but it's very complex. And yeah, adding and deleting files can lead to a drastic reorganization of the tree, which also pays into that complicated analysis process and analysis, or this complex structure. Yeah, maybe we'll stop here. Like, this exists. The SleuthKit does it for you, but the SleuthKit doesn't give you more information about the B tree. Yeah. Okay, but something that is not on the analysis slide, of course, is if you want to have a look at the file name, for example, you can just have a look at the file name attribute, which contains the name, which the MFT tree entry can also have multiple file name entries, attributes, where you can store additional names. Yeah, so you can also, in case you want to keep it simple, check out the file name attribute for the file name. Okay, there's a question in the chat. Since format recorded is in UTC, if you wanted to manipulate timestamps by changing the system time, manipulation should not be possible, right? Since everything gets recorded regardless of using tools like the one you mentioned earlier. On a server level manipulation, I know manipulation is possible. I don't know if I get the question correctly. So of course you can manipulate timestamps. You can also change the system time. The format I mentioned, the only thing it tells you is that timestamps are stored in nanoseconds since this specific date. But it's actually independent of system time or manipulation or something like that. The only thing that it tells you is if you use a hex editor to view these timestamps and you extract these timestamps and you want to recalculate the time of the timestamp, then you have to be aware of the way it is stored, the format in which it is stored. That's the only thing that it tells you. Manipulation is absolutely possible. Okay, let's talk about application data. This is also the last category that we have for NTFS. I think I told you a couple of weeks ago, 2 weeks ago, that application data usually refers to logging and journaling and stuff like that. And in NTFS, other than in FAT, you have logging and journaling and quotas and statistics and stuff. Be aware that all of that isn't essential data, so it's non-essential data. And NTFS is, as I said, a journaling file system, so changes of the files are logged to a specific file in the file system. What it does is it logs when files are changed, when files are deleted, when files are created. And I think I told you before that the system, this journaling and logging system, was basically developed in order to restore the current state of an operating system after crashes and stuff like that. So for automatic recovery after system failure, then in cases the system crashes, but the journal logged that a certain action happened before that, then these operations are executed in order to restore the status of the operating system. And we have two important journal files in NTFS. We have the log file, which is the NTFS journal file that records changes to metadata, and we have the user journal file, which provides a higher level summary of changes to the volume. And so in FAT, for example, we don't have something like that, but in NTFS we have that. Okay, that's already it. Let's summarize the most important NTFS processes. So in case a file shall be created, let's call it file1.dat. Let's say it's 4,000 bytes of size. And it shall be created in an existing directory dir1. Then what happens is we have a cluster size in this example of 2048 bytes. You don't have to worry about the bytes too much. What happens is, or what we have to do is we have to read the boot sector first. Then we have to, with the information from the boot sector, we have to find the start of the MFT entry. Genau. Yes, sorry. Switch to German for like a second. Okay, read the boot sector, find the beginning of the MFT, read the size of an MFT entry in order to process the MFT correctly. Then we search for the entry for the MFT itself. Yeah, and then an entry in the bitmap attribute is assigned to the file. So we flip a bit in the bitmap attribute in order to give the information, the system the information that this cluster now is occupied by a file. Then a standard information attribute, file name attribute is created and the timestamps are set. Then the clusters that are used for the content of the files are assigned in the data attribute. Then we can write the file content to the newly occupied clusters. We search in the index structure in the root directory for a directory named dir1. So where we are currently, we did that. Now we are here in the root entry. We search for dir1. We allocate or we write the file that we want to write in the clusters in the directory or assign it to directory number 1. We have the data attribute with the cluster run list and the contents in the clusters. Yeah, and we have to, of course, create a new MFT entry for file 1.dat in the root directory, and we already did in the MFT. And in cases, or because we have it in a directory, also the B tree is reorganized and the timestamps of the directories are updated. So this is how a file is created in NTFS. And in cases the file shall be deleted, the boot sector is read again. The MFT, the corresponding MFT entry is found in the MFT. The MFT entry is read out. The directory dir1 is found in the root directory. The timestamps are updated in the directory, in the entry for the directory. The entry for the file in the directory is removed. The tree is reorganized. The MFT entry for the file foo.txt is marked as deleted. We change the entry in the bitmap in order to tell the system that the cluster now is free again and can be used for other files again. And so in cases where the file is non-resident, which is the case for foo.txt, we deallocate the attributes, so the data attribute for file 1.dat, and that's it. The file is deleted, and as I told you, the MFT contents are not overwritten or wiped or anything like that. Also, the cluster content isn't wiped. So after the deletion process, there's a good chance that we can still reconstruct the file, but after a certain time, the MFT entry and the clusters are probably reused. And that's that. So much for NTFS. Today I'm very timely, and we have still a couple of minutes for questions if you have any. Okay, there's a question. You said that everything is a file in NTFS. Maybe I missed it, but are directories also represented as files, or are they just derived from the tree structure? Is that tree structure also a file, or is that in MFT? Okay, so the directory structures, they are stored in these B-tree files. Yeah, that's the directory thing in NTFS is the complicated part. So the directories or the structure of the directories is stored in these B trees, and the B trees they have these, or there are these B tree attributes that tell you something about the structure of the directories. And these are attributes in an MFT file. The root directory, which is a file in NTFS, because everything is a file. And you can find the root directory in the MFT in entry 5. And the MFT entry of the root directory has these these B-tree attributes, which store the structure of the directories. But you also, for each directory, you have an additional MFT entry because you also have like timestamps and names for them. And I think, when I remember correctly, there is a flag in the MFT entry that is set in cases the MFT entry belongs to a directory. So you have two data structures. You have the root directory, which tells you everything about the structure of the directories, and you have for each directory an MFT entry, which tells you the name, timestamps, additional information. Does that answer your question? Okay. As I said, in the carrier book, you can also find more information about that. To be honest, I analyzed like everything of the NTFS file system like manually a couple of years ago because I wrote a parser for file systems. But actually, the B-tree thing, at least back then, was so complicated that I skipped it. But I don't want to scare you. I'm just saying, like, this is the part I am least familiar, yeah, with. But all the information can be found in the carrier book in cases in case you want to read more about it. Yeah, maybe yeah. I'm probably not very good in explaining that part of NTFS, but carrier might be. Okay, any more questions? Okay, there's a question. Searching for file in Windows NTFS takes an eternity, but on Linux, just a couple of seconds. Does that have to do something with the file system, or is that just a bad implementation of the search? Oh, I guess it's a Windows problem. I don't think it's an NTFS problem. It's probably because Windows is so overloaded with stuff. I cannot answer the question, but I guess it's a Windows problem. Yeah, and Carrier Book is actually the Bible of digital forensics, of file system forensics, at least for the older file systems. So for newer file systems, I think I told you once, it's complicated. because nobody updated the file system forensics book in the last 20 years. I mean, writing a book is also like huge amount of work. Yeah. Okay, any more questions? I mean, I just to be transparent with you guys, like the B-tree stuff, I never analyzed it manually myself, but Carrier did. Okay, in cases there aren't any more questions, I would like to thank you for your attention. And next time we will talk about the ext file system, and then we're basically done with the file system stuff. Next time will also, or I will also distribute the links to you in order for you to evaluate the lecture. And I think Roman will hand it out to you already on Thursday, so the link to evaluate the exercise. And I would like to kindly ask you to evaluate and yeah, tell us what you liked, tell us what you didn't like. I know we had some organization problems because there are so many people interested in digital forensics, which is pretty cool, but which is also like difficult to handle for two people, basically. Okay, so yeah, just that you know, next Thursday you get the evaluation link from Roman. Please evaluate us. Please be kind to us. But yeah, of course, give us feedback. We appreciate it. And yeah, thanks again for the attention today. Have a nice weekend and see you next week. Bye bye.